And then you can have it as a resource. So, okay, well, if there is nothing that you want to go through in terms of the past stuff, then why don't we then continue on? So I think it makes sense in this case. I mean, we did the interpretations of quantum mechanics for last lecture, but I mean, that was basically very qualitative. So I think there's not really that much really to revise, and it doesn't really connect so much with what we're going to talk about today, which is composite systems. So I think what I'll do is I'll just simply get into the next set. So full screen. Okay. Right. Okay. So we're talking about composite systems for today's lecture, and basically what that means is that if there's more than one quantum system. So everything that we've talked about so far is really about just basically like one quantum system. So it might be like one atom or one photon or one quantum object. But in this case, what we're going to look at is sort of multiple quantum systems. And in fact, this is actually what really gives the power of quantum mechanics, because what you'll see is that actually when you have many systems, it will the kind of the size of the system of the vector space actually grows exponentially. But we'll get onto that in a minute. Okay, so work out controls here. Gone out of full screen, sorry. Not quite used to remote learning, teaching at the moment. Okay, so yeah, so this is basically what we've been talking about up to this point. So we've been talking about basically just kind of one quantum system, and we've kind of mainly looked at this kind of two particle or two level system, so like a qubit up to this point. More generally, you can have like d levels like this, but basically we've been looking at just like one quantum system. And so the question now is, all right, so suppose we bring together two of these things. So now there's like two of these d level systems. So we're going to bring in Alice and Bob as like two people that are in possession of these two quantum systems, and basically see what happens when you kind of combine these two things together. So yeah, so in general, like one quantum, on one quantum system, we know how to write down the wave function. It looks something like this. It's just some kind of vector that's a sum of these d different levels. And so we've got levels going from 0 to d minus 1. And these are normalized in this way. Okay, so let's see how to turn the page. Seems like a very simple thing. I have to exit something and turn the page. Okay, all right. So basically what happens when you have more than one system is that basically you have to count all the possible combinations of the states that the two systems can be in. So for example, here, so we've got like a 2d equals 3 level system. So say atom here has 3 levels. So there's like, 1, 2, 3 like this. And there's 2 of them. So Alice and Bob each has 1, right? So there are a total of like 9 different combinations that you can have because, well, I've listed them all here. You can have just the, the first system in this state 0, and the second one in 0, or 0, 1, or 0, 2, and all the way up to 2, 2. Right? So what you basically have is, in the end, this kind of 9-dimensional kind of system. And so, because when we do quantum mechanics, we basically always have to write down all the different distinct states that we have, right? So these are all distinct states. So we basically, in this composite system, we've got a 9-level kind of system effectively, because there are 3 times 3 combinations of different distinct states. And each of these things are distinct in the sense that they can be distinguished from each other. So for example, if you did a measurement, then you can definitely tell the difference between, say, this state and this state. And the way that you would tell the difference is, of course, if Alice has this first qubit here, and so if she measures the state in level 2 in this case, and level 1 in this case, so Bob in each case actually has the same state, but if they come together and look at their results as a combined result, then you can definitely tell the difference between, say, these two. These are 2 distinct and different states, right? So so how we kind of write that in quantum mechanics or mathematics, I guess, is this so-called tensor product thing. And basically, tensor product is just a construction to sort of say the thing that I've drawn as an example here. Essentially, it's saying that you can make this particular type of combination, and each combination is basically a different element, right? So we have this symbol, this O times thing, and basically that's sort of saying that we're looking at combinations of different states here. So basically, it doesn't make sense to just do regular times, because how do you multiply 2 states together? It's not really a kind of a quantity here in this case, but you can create this tensor product, which basically means that you are looking at every possible combination of these vectors, right? So this is like kind of the proper way to write it, but often physicists get lazy and we want to abbreviate things. So often I'll start to write it like this, where I just omit the tensor product and just kind of say that it's implicitly it's a tensor product, meaning that we're looking at different combinations of this. Or we can even abbreviate it further and write it something like this. And basically what's happening here, what I mean by this notation here, is that in this one, what I'm doing is I'm considering basically these 9 states to be all like individual states. So basically, what I'm doing here is I'm kind of calling this one, the state like 0, 0. Okay, maybe no, I don't want to annotate now. Okay, so this state I'm going to call like the state 0, 0. This state I'm going to call the state 1, 0. This state I'm going to call 2, 0, and so forth, right? So I'm basically considering these combinations as already being states which have a unique identity, and then the way that I name them is, I can name them in any way that I want, but I'm going to name them just with these two numbers of like NA and NB. This one is, so, when I write it like this, I'm saying that it's more like, this is a particular state. Whereas if I'm writing it like this, then what I mean by that is that it's still got this sort of, you can see the underlying structure of basically what made up that state. When you write it like this, or in terms of the tensor product like this, what I mean by that is that, these are originally two different quantum systems, but I'm going to combine them, and then they're going to sort of form one kind of quantum system eventually. Okay, is that clear? Maybe I sort of rambled on a little bit too much there, but okay. Okay, good. All right, so let me attempt to turn the page. It's proving challenging. Okay. Okay, here we go. Okay, now I've got to delete all this stuff. All right. So, what's a general quantum state that you can write in terms of this two-party system, right? And so, just like we did before, basically a quantum state can then be made up of any kind of superposition of these tensor product states that we just defined. So, so in the previous case, we had these 9 states here. So these 9 states, and those 9 states can participate in a superposition. And so what you're going to have in general is a vector which consists of these 9 different states, right? So this is this thing here is a psi is a 9-dimensional vector, and of course I could just write it as a 9-dimensional vector, but just so that you can see the underlying structure, often the way that we write it is in terms of these coefficients, like here, A, NA, and B, where these ones run over the dimensions of the subsystem. So NA runs from 0 to D minus 1. This is just Alice's dimensions, right? So 0 to D, so that's D dimensions for Alice, and NB runs between 0 and D minus 1 again. And so, I mean, if you were to write this, you might think it's written as a matrix, and indeed you could write it as a matrix. So you could write it as, something like this A is, it's not some kind of 3x3 matrix like this, right? So the dots just the numbers, right? So in this case, it'd be 3x3 matrix. But actually, it's a little bit more helpful just to always distinguish between, like what's basically happening quantum mechanically. So quantum mechanically, we basically always picture these things as vectors, right? So these are kind of vectors. And then what we discussed before is that like things like observables. So remember those Pauli matrices and any other observable, we associate those with matrices. So so actually, even though, yes, you can write this thing as a kind of a matrix, I mean, you can always, of course, rewrite this 3x3 matrix kind of course, as a vector. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, depending on the context, I think it's more helpful in the end just to still consider this thing as a vector, even though these coefficients look like a matrix, basically because, this state is ultimately still a vector. It just so happens that it's consisting of like 2 subsystems. That's its origins, but actually, fundamentally it's still can be written as a vector. So probably I would suggest that you still think of this thing, this psi, still as a vector, even though these coefficients kind of look like a matrix. Okay. Now, yeah, and as with any state, this state always is normalized, right? So the state, these coefficients that we just talked about, the modulus squared of them, this modulus squared, the sum of all of them have to add to 1. And this is the same rule that we've already encountered. Now, the only difference here is that, now we've got these double sums. But again, I mean, this double sum, of course, we can, basically, again, just consider sort of as a vector, because essentially this is just a way of labeling 9 different elements here. So there's basically d squared elements here. And so it's just a sum over these d squared elements. And maybe, it's in the end, it's basically the same story as what we encountered before. These d squared elements, you just add the modulus squared of each of these elements together, and then they should all add up to 1. Okay, and right, and yeah, and just in terms of the notation, yeah, so sometimes I just omit this tensor product here. So sometimes I'm going to write it like this, or again, if I just consider this combined thing as some kind of state that is labeled with 2 numbers here, then I can just sum over this. So basically, all of these things, like this one, and this one, I can, for me, they're basically exactly the same thing, just slightly different notation. And, just the way that I happen to write it might be just based on the convenience at the time, but fundamentally, they're exactly the same thing. Okay, all right.
Professor,
Sure, yeah.
like I just recall that isn't it the tensor product is also written as the Kate-Bra notation, like?
Right, yeah. Yes. Yeah, good question. So that's did we call it tensor product, or was that, didn't we? No, we called that outer product, didn't we?
Yeah, outer, but isn't, because I thought outer product and tensor product are like,
Yeah, well, yes, you're right. I mean, in the sense that, this is why, like, you can write, this A as a kind of a matrix, right? And so basically we learned that the outer product is basically like a matrix, right? And then here also, this is a matrix, even though I sort of said that this is, you should kind of think of this as more like a vector rather than a matrix. But of course, well, you've got a bunch of numbers and you've got 2 coordinates, and well, that's a matrix, right? Now, yeah, so I think in the end, yes, they're in this example, they are basically the same, but then the roles that they play are quite kind of different. So so one difference here is that, for example, if we had like 3 quantum systems, what's going to happen is that there would be like a tensor product of 3 things here, and then this A would have 3 labels, right? Okay, then it's definitely not a matrix. It's kind of like a cube, right?
yeah, right.
Yeah, and definitely that structure does not exist with the outer product, right? So the tensor product might be a little bit more sort of general in that way, and and so, that's one point that I think in general, this tensor product, we could have as many as we want. The outer product, we only really ever have one. And I think ultimately, yeah, it's to do with the roles that the things that these quantities kind of play. And so, as I was saying, this thing, although formally you can write it as a matrix, but in terms of the role that they play within quantum mechanics, it's actually still really a vector, because the way that we basically visualize, or not even visualize, but understand quantum states, is that basically they are particular vectors in this Hilbert space, right? And so, this is why, even though probably mathematically these are rather related concepts, but actually in a quantum mechanical concept, I think it's better to just sort of stick to the idea that, okay, fine, this is formally a matrix, but it's better to think of it more as a vector. Whereas the outer product case, of course, you could rewrite the matrix like as a vector if you wanted to, because it's just rearranging numbers. But in terms of the roles that it plays, I think it's better to think of it like an operator, and then in that case, it's like more like a matrix. So I don't really have a really great, I think, answer for your question, but I think for me that's kind of the rationale for why it is this way. Maybe a mathematician could answer your question a little bit more sort of rigorously, but like in terms of from the physics point of view, I think that's sort of the importance of, or the difference in roles of the outer product versus tensor product. Okay, any other questions? No. Okay, so let's keep going. Yeah. So right, so let's just look at a simple example. So I mean, the 3x3 was already a kind of an example already, but let's look at an even simpler example here. So if we've got 2 qubits here, then we've got each Alice and Bob each has a qubit. They're each 2-dimensional. And so basically the total dimension of the combined space is d squared. And so it's 2 times 2, which is 4. So the states that we're going to have are basically all the different combinations. So we're going to have 0, 0, 0, 1, 1, 0, 1, 1. And basically the states that you could possibly have are, again, any combination of these 4 states. So these A0, A01, these are some complex numbers that you can choose sort of arbitrarily, and these are normalized. Right? So these have to be always normalized, meaning that these coefficients, the modulus squared, adds to 1. Okay. So yeah, so you can kind of see that, well, in general, it's like this double sum, but in this case, it's well, much smaller system. Okay, and so
Professor, do you mean like for
yes.
the formula, should it be like A00 ket 00 plus A01 ket 01?
Sorry,
Or
so just so that I know what you mean. You mean what? A00 ket like 00 like this? Sorry.
and for like the next one is 01 and the
Oh
next
yeah, right. Yeah. Sorry. Yeah. Typo.
oh
Yeah. Typo. Yes. So sorry. This one should be 1. This one should be 1. Yeah. Sorry about that. Yeah. Okay. Thanks for picking that up. I'll try and correct that for next time. Okay. All right. Oops. Where are we going? Okay, so let's kind of look at another sort of special case, I guess, which is, we'll also look at the case for qubits, but let's look at this case of independent states. And so physically, what this kind of means is that you have two quantum systems, but they're basically, they never talk to each other. They've never sort of come together. They've never interacted. They really don't know that each other sort of exists. And so the question that I have on the slide here is, so suppose you had two qubits like this, and they're on sort of the opposite ends of the Earth. And can we form a composite system between those two? To form a composite system, do we need to sort of really like bring them together and make sure that they're really like one quantum system? And basically the answer to that is that yes, you can actually form a quantum system between any two quantum states that you actually like. So even if they've never interacted or anything, it's purely a matter of like what you choose to take into account in your calculation. Basically, it's a question that of like whether it's kind of important to take into account or not. And for example, in this case, if basically these are completely independent, then what should happen is that taking into account, so imagine that you're Alice and you're there and you're doing some experiment on this qubit here, and you're wondering basically whether Bob's qubit, which is on the other end of the Earth, maybe in Brazil or something, whether you need to take that into account into your calculation or not. And intuitively you would think that you don't need to, because, well, it's very far away and nothing got to do with my qubit, which is over here. But how do we take that into account mathematically? And so basically what happens in this particular situation is that, well, yes, you do still form this kind of composite system, and you form it in exactly the same way as you did, as I kind of showed you before, we're using this tensor product. But the only difference is that basically each of these underlying states here are actually the kind of states that you would consider sort of separately for Alice and Bob themselves. So for example, in this example here, you have basically the state here, which is going to be just a superposition, just like we encountered already in the earlier lectures. And then also Bob has his one. And basically you just form a tensor product between those two states. And if you do that, basically you do get a state eventually. And so that's basically what you do. And then you can write it out in terms of the state that we had before. And you can write it out like that. But basically what happens is that instead of a more general coefficient here, sorry, just a sec. Instead of a more general coefficient here, so like previously what we had, so previously, if you remember, what we had was something like this, right? NA, NB, right? And this thing here, when you have the, when you bring just two systems together, is actually a more specific, like, this structure here is not as general as what I wrote in the previous slide, right? So if you have this A, NA, and B, this is like a general set of 9 complex numbers, right? But here, if you have A and A times B and B, this is actually not as general as this this kind of matrix that we had in the previous case. So what you actually end up with is a more specific kind of state, right? And so just to give you a more smaller example, so for qubits, if you've got 2 independent states, then what would happen is that it would be the tensor product of the state for the first qubit and the state for the second qubit, like this. Let's see if I've got any more on this on the next slide. Okay, no, I don't. Okay, so so basically this is basically showing that, this is, or rather maybe a good way to think about this is that this is quite similar to the idea of independent probability distributions, right? So when you have independent probability distributions, so for example, if you've got a function of 2 variables, so if you've got like a probability distribution of P, X, Y, right? Now, that basically means, you've got 2 probabilistic variables, P, X, and Y. And, if the variables are correlated, then, you'll have a particular distribution for this function. But, if you have an independent, so maybe P dash, if you've got an independent set of variables, then basically the probabilities kind of appear as this product. And so in quantum mechanics, it looks very much the same, actually. So this kind of tensor product notation, or tensor product structure to the quantum state is really just like how you have like independent probability distributions. But of course, so in general, this thing is not the same as a completely general like quantum state. Well, okay, this is more general. In a more general quantum state, you'd have A and A and B, and B, as we had on the previous slides, right? So basically, these 2 things are generally not the same, but of course, a general quantum state can be an example of this kind of independent state. So basically, it's like in terms of a Venn diagram, you have independent states like this, and then the general states are the full set. Does that make sense? Okay, all right. Right. So, so that's basically how you form these types of composite systems. Now let's talk a little bit about how measurements work in this system. So I think we'll go on to talk about how things like observables work and other things like this later. But just to start off, let's talk about measurements. So what you've kind of learned already carries over pretty much for this composite system case. So the main thing that you basically have to always realize is that, when you bring together these 2 composite systems, you're going to be always measuring in this kind of larger Hilbert space, right? So for example, for 2 qubits, you're going to have 4 states in total. And so that means that they're going to be like 4 measurement outcomes, right? So, after all, when you write down your quantum state, you know, you can, in this composite system, you're going to be, you know, writing down the measurement. Sorry, you're going to be writing down the state itself in terms of a sum of these four states. And so it's kind of natural that when you go and measure that, you're going to have 4 different measurement outcomes. Now, the probabilities that you're going to get just depend upon, again, the coefficients. And so it's basically exactly the same rule as we saw before. It's just this complex modulus squared of the coefficient. So we can kind of visualize this just in the same way. Here now we've got like 2 particles going into our measured machine here. And these are the outcomes. There's going to be like 4 different outcomes. So in this output, you're going to have like 4 different results. And as before, it's possible to have actually you know, different measurement bases in this 4 state system. It just so happens that these 4 states just come about from different, you know, combinations of the 2 particles, but you know, there's still going to be 4 different outcomes. Okay. All right. So even though, so that what I said there is actually pretty general. Okay, so maybe this is the way to do it. Okay, still learning how to do this. Okay, so on time. Okay. So yeah, so basically what I said there is actually pretty general, but what happens actually quite often is that the measurements are local. Okay, and what does it mean for measurement to be kind of local? And basically what this basically means is that, you know, remember Alice has like one of these particles and Bob has one of these particles. So even though, you know, previously I said that in general, you're going to have basically these 2 particles that go into the same machine. And indeed, you can have such measurement devices, right? But a more common kind of situation, just because of practical considerations, you know, I mean, if you're going to measure 2 particles, the most natural kind of measurement that you'd kind of end up doing if you're an experimentalist is that, okay, well, I got 1 particle here, so I go and measure that particle, and I got another particle here, I'm going to measure that other one, right? And then you know, you do separate measurements for each particle, right? It's a little bit harder to imagine, although, you know, we can talk about this later. A little bit harder to imagine how you actually measure these 2 particles kind of at the same time and kind of get measurement outcomes, but it is possible. But this is a more natural kind of situation that you often end up doing. So essentially what happens is that, so if Alice goes and measures her particle, so this particle goes into her measuring machine, and then, you know, say this is a qubit, so there's going to be like 2 outcomes. So there's 2 readings on the output here, and so there's going to be like 2 output cases. So there's going to be S0 and S1, and these are the states on Alice's side. And Bob also measures his particle, goes into the machine, and has 2 outputs, S0 and S1 too. And these ones could be in like different bases. Right? So basically what you eventually get is Alice and Bob, they are both they both get their measurement outcomes. So, say on a particular situation, Alice gets 0 and then Bob gets 1. Then in that case, that would be one of 4 possible combinations, because each person has basically 2 possibilities, and then 2 times 2 is 4, so you get these four different outcomes here. And the original state and the probabilities that you get for each of these outcomes would simply depend upon well, the original state that you had here. So if you've got some superposition of these 4 states, then you'll get probabilities with the usual mod squared kind of rule. Okay. Right. So that's how measurements work. Now let's introduce a little bit of mathematics here. So we can define like measurement operators in a kind of a similar way to how we constructed the states. And basically what that means is that we'll have a tensor product of these measurement operators too. So what does that mean? So suppose we've got, so what's happening in this particular situation is that Alice is measuring the the particle in her machine, and Bob is measuring his particle, and there are the 2 outcomes for both. And we learned previously that each of these measurement devices we can associate with these kind of measurement operators, right? So we learn about measurement operators. So these measurement operators, this MN has and then if we've got 2 of these, we better put a label on for Alice and Bob. So Alice's measurement process we can describe as MNA, and then for Bob's measurement process, we'll put a different sub-label here, M. We'll put a B here for Bob. So for Bob's measurement, we'll have M sub M B, right? And when we want to write down what the measurement is for this combined system, then basically what we do is we kind of take the tensor product of these 2. And again, basically tensor product basically means that you're going to look at all the possible combinations of the outcomes that can happen. And so when we have the measurement operators, remember what we do is we have so in the case of just Alice, basically the 2 measurement operators were either like S0 or S1 right? So that was the case for Alice, and something similar for Bob. Now what we do when we look at the measurement operator for the combined system is basically follow the same rule. And so what we do here, so this thing here again is, I've got, this is, for example, equivalent to the S0 tensor S0, or sometimes I'll just write it as S0. Okay. So basically that thing there is the same as just the tensor product of the 2 outcomes. This is when both Alice and Bob get this S0. And then if we can construct the ket vector for it, then we can also construct the bra version of it. So that's just the conjugate transpose vector. And this basically forms one of the outcomes. And so I didn't quite write this, but basically this one would be what I would call M0A times M0B. Okay. And of course, so this one would be M0A times M1B and so forth. So these would be basically the four measurement outcomes that you can have for this composite system. And so right. So then okay. So maybe just before doing this, maybe we can just do a quick example. So so just to do an example here. Get a whiteboard. Okay. So for example, let's say you know, I had a state that was let's say A00 of 00 state, A01 of 01 state, A10 10 state, and A11 of 11. And so when we do the measurement operator, what we do is, so we have the measurement operator, and suppose we are, you know, after this particular example of M0A, M1B. And so basically what that is 0 tensor product 1, and then the conjugate version. And so sometimes it's confusing to know which state is what. So I'm going to put Alice and Bob there. And another way to write this is just simply 0, 1, and 0, 1. Right? So if you want to work out what happens after a measurement, then basically the rule is always the same. In fact, actually, this measurement operator here, you can even construct a sort of a composite measurement operator for the whole system. So, for example, I might write M01 as this sort of composite system measurement operator. And in this case, these measurement outcomes are maybe more generally. So I could define the composite system measurement operators NA and B as just NA. Yeah, sorry, superscript B there. Okay, and then so if you wanted to say work out what the probability or the you know, resulting state is, then what you do is you just, of course, again apply this M01 to the state. So this is zero, 0, and then 0, 1. I'll write everything out. And over here, basically the orthogonality rules, just like before, always follow. So in all these cases where we can view this thing here as it's going to take, you know, combine with the inner product of each of these, right? So 0, 1, and 0, 0, these are orthogonal. So this is going to disappear. 0. So this first term will be 0. This second term will be A0, 1. Oh, whoops. Wrote exactly the wrong thing. And like all the other terms, 1, 0, all these ones will be just 0. So all these are 0. And so eventually this, and then this thing is just 1. So A0, 1 will just turn out like this. And then if you want to work out the probabilities, then so the probability of that outcome is just the same as what we've been doing before, which is psi M01 dagger 01 psi. So it's basically just the this state with the complex conjugate transpose. And this is just A01 star, sorry, modulus squared. So, you know, basically it works in exactly the same way as we're used to. And maybe, you know, just to be a bit clearer on why these were orthogonal. So let me just expand upon that. So I said that, you know, things like, well, okay, so maybe I can sort of do the general case, right? So MA and B. So in general, this thing is only the same if NA, MA. Basically, this is only one if basically these things are exactly the same, right? So basically, you know, so in the example that I had before, only the term like 0, 1 for both NA and B and MA and B gave 1, because basically the only time that you have this product of these two Kronecker deltas being the same, so both basically this has to be equal to 1 and this has to be equal to 1, then then it's equal to 1, right? And the reason why it's this tensor, sorry, Kronecker products delta is because you know, NA and B is equal to whoops, pen is dying. NA out of product and B out of product. And so when you do this, then what's going to happen is that you're going to have basically, you know, NA out of product and B times by MA tensor product MB, and basically this one, you know, takes the inner product with that one. This one takes the inner product with that one, and then this this NA with the MA gives basically this term, and this NB with the MB gives you the second term. So basically this is only equal to 1 if basically both of the states are the same. And this generalizes to any number of indices. This is just for 2 indices, but for any number of indices, this is going to be true. Is that fine?
Like why we can't do the inner product of the MB and MA in the middle?
Why we can't do the inner product of which one?
the because we are doing like inner product of NA and MA and MB and MB, right? So
Oh yes.
so like why we can't do this in
Oh, like why you wouldn't, or why you can't take the inner product of like NA and MB, for example, like you're saying like this one and this one.
yeah.
Well, I think that's just how tensor products work. So, you know, I think ultimately, like basically these things are in kind of different spaces. So, you know, in the same way that I think, you know, you can't take the inner product between two vectors, like two you know, regular vectors. So, you know, you can't take the inner product between basically A and B, but you can take the inner product between A and B, right? And I mean, the reason why is because basically, you know, these two are, well, the inner product have to be sort of compatible with each other to come together to produce a number. But in the case of this NA and MB, you know, these are different vectors in different spaces. So I think you simply cannot, you know, they might even have different dimensions actually. So in the case that we looked at, we were always looking at the case where the dimensions of A and B are the same. But, you know, you could have a situation where Alice has a dimension 2 and then Bob has a dimension 5. Now, you cannot take the inner product between things of different dimensions. So I think they're just not compatible to create an inner product. Yeah. Okay. All right. Then let's go back to the slides if I can find my way back. Okay. All right. So where were we? Right. Okay. So that was how, you know, measurements work in this for this composite system case. Now let's go back to that example of an independent state. So remember a couple of slides ago, I was saying something like if you have a state and, you know, like two states and they're completely independent, then the two states you know, form this kind of form like this, and basically you know, just like how you have independent probability distributions, then in that case the second, you know, well, they don't influence each other at all. So let's have a look at that again and make sure that that is the case, right? So for example, you know, let's again look at this case where, you know, you had Alice and Bob, and then, you know, Alice has this qubit, Bob has that qubit, and, you know, they're supposed to be completely independent. You know, maybe this is in China and this second one's in Brazil, right? So they're nothing got to do with each other. Now, it would be very weird if somehow, well, even though they're supposed to be independent, you know, the results of this detector somehow were correlated or, you know, did something in conjunction with this other detector, right? So if they're supposed to be independent, then the results on this detector should only depend on the properties of this particle, right? And the results of this detector should only depend upon the state of this particle, right? So that's basically what we are gonna, you know, this is what we expect. if we have independent states, okay? So let's work that out. So we start with this independent state like that. And then let's figure out what is the probability of me getting, say, P0, which is, that's basically all the probabilities where you get 0 on the first detector, okay? And so that can actually happen in 2 ways, because in this composite system picture, then you can get 0 here, and then Bob could get 0. Remember, Bob's in Brazil, you know, not supposed to influence our one, but he's in Brazil, is getting 0, or you could get 1. And either way, that would count as a measurement 0 for Alice, because basically in either case Alice gets 0, right? That's the only thing that we care about at this point. So so the probability of Alice getting 0, full stop, is P0 plus P0, sorry, P00 and P01, okay? And so we've got our wave function. And for this case that they're independent, the coefficients of these states look like this. And so that's a special case. They have a sort of a special structure because they're supposed to be independent. So they're always going to be multiplying, you know, in these two pairs like this. A0, which is that's the number from here, from the first state, and B0 is the number from the second state. Okay, and so we already worked out, you know, just in our example, how to work out what the probabilities are. So I already told you basically before that the rule is simple. It's just to take the coefficient and then do the you know, modulus squared like this. Or you could do measurement operators like I just did on the whiteboard. And then, so the outcome for 0, 0 is this one, and the outcome for 0, 1 is this one. So we take the modulus squared, okay? And if we add them, then we can just factorize this A0, and then we'll get B0 mod squared plus B1 mod squared. And of course that, because all states are normalized, this thing is equal to 1. And so that's just A0 mod squared. And that's exactly the result that we expected, because it's completely independent of Bob's state, right? So the probability of Alice getting 0 is A0 mod squared, and doesn't have any B's in it at all. And so that shows you that it's basically the same as, you know, as if basically, you know, you did a measurement just alone. So if Alice just went into her laboratory, did the measurement, got the results, you know, that's the result she would get. Or she could, you know, coordinate with Bob in Brazil, ask him what measurements he's got, you know, do it this more complicated way. Either way, they will get the same result, basically because they're independent states. So it doesn't really matter that you include Bob's result or not, because they're independent. So, you know, this is basically why you can you know, you can kind of choose what you can include in your quantum state, right? So let's see if I've got a slide on this. No, okay. So yeah, so maybe the point that I'll finish up on today is that, you know, I mean, the universe, you know, is basically full of particles, and ultimately everything is quantum, right? So everything from, you know, a human body to all the planets and the stars, you know, everything's made of atoms, and, you know, microscopically everything is determined by quantum mechanics, right? So you can, in principle, write down a wave function of the whole universe, right? And the reason why you don't have to do that each time is basically because of this property that, if you have an independent state, it doesn't matter whether you have it there or not have it there. So, you can have the, wave function of Jupiter here, and it wouldn't really matter that you had it because basically, what's happening on Jupiter, doesn't really affect what you're doing like in your lab here on Earth. So you can have that wave function, but basically it wouldn't really do anything. Just like in the same way that basically the probabilities that Alice measured, doesn't depend upon Bob at all. Okay, all right. I think maybe that's a good place to leave it. Any questions?
Professor, is it possible for us to have like something like practice exam or things like that?
I don't usually have practice exams, but maybe I can just give you last year or one of the past year's exams.
Yes, that would be great. Thank you.
Yeah. But I mean, they are going to be very similar to the homework questions. So, the first thing that you should try and do is make sure you can do all the homework questions, and we'll go through. We'll have like a revision class where we can go through the any topics that you want to go through again. Yeah, so we can do it like that. Also, really should get on to the assignment. Have you guys given any thought to what assignment topics you might like to do?
Not really started yet.
All right.
I
Okay,
think
I guess you got midterms coming up, right?
I've looked at the website where we can build the quantum circuit, I think.
Okay.
Yeah, and there's like the symbols, and yeah, you can just it's basically like building like Legos, something like that.
Right. Yeah. So if you want to do that one, then that's great. Just I don't know, just let me know. Maybe you guys can send an email, give it a little bit of thought, and then just send me an email of like what topic you like to do, so we can kind of lock it in and at least sort of make a start on it. I know you got midterms coming up, but we'll get on to doing the presentations after that. So yeah, I mean, not straight after that, but sometime in the second half. Yeah. Okay. All right. So
do you want to like put the exam sometime before the week of March 29th? Because I think
well, again, yeah, it's
session-
up to you guys. I'd be happy to do that. Just because we're sort of in this situation. But
I might need more time because I think one of my exams, like the constructor just told us today that he's gonna tell us more about it before next lecture. So
okay. All right, okay, we'll leave it at the date. Yeah, it's totally fine. It doesn't bother me either way. So
we'll still like take March 29th, right?
Sorry, what was that?
So we are going to take the midterm at March 29th, right?
Yes, March 29th. Yeah.
Okay, that'll be great.
As discussed before. Yeah.
Okay.
All right, then we can leave it there, and I'll see you guys on Thursday.
thank you, Professor.
Right. Okay. Bye.